Whenever I have an Active Directory pen test, most of the time I see LDAP-S and HTTPS, but I've never asked myself where those protocols got their certificates. Maybe those certificates are self-signed or signed by a public trusted certificate authority or a local certificate authority. And since we are dealing with Active Directory, it's usually going to be ADCS. Active Directory Certificate Services. That's why I have spent the last 3 months learning about ADCS, how to attack and abuse it, and creating this full course. In this course, we're gonna start by building our own ADCS lab and then explaining the key elements to understand how it works, like the PKI, public key infrastructure, what is a certificate sign request, a template, PKInit, and so on. Then we will move into how sysadmins use ADCS to secure their local infrastructure, and at the end, we're gonna dive to the most interesting part, which is abusing those misconfigurations that are left by sysadmins. To get a better understanding, we will create those misconfigurations in our lab, and then we're gonna abuse them to escalate our privileges. All the modules are well organized in this course. Feel free to jump to any module you want. And finally, if you want to support this channel, please don't forget to subscribe, like this video, and leave a comment regarding any mistake or improvement that we should implement in our future videos. Enjoy! To really understand ADCS, I decide to spend a couple minutes on understanding what a PKI means, a public key infrastructure. I'm going to start from an example where a user wants to connect to a website using his web browser. If we are not using HTTPS that is based on SSL TLS, then anyone between me and the server can intercept and read data in clear text. So in this case, SSL TLS are used for data protection, right? But how? Quickly, what is the difference between SSL and TLS? Well, TLS is just a maintained version of SSL, because in 1995, SSL was introduced by the Netscape company, and then in 1999, another corporate called EETF took that SSL protocol and maintained it and renamed it to TLS. So basically, TLS is a more secure and maintained version of SSL. So how TLS protects data? First of all, TLS is not meant to prevent the capture or the interception of data. Instead, it wants to protect it. So even if you capture it, there's nothing you can do with it. Let's illustrate a client and the server. The clients want to send data to the server. Without encryption, anyone in the same network that this data passed through can intercept it in clear text, read it, and tamper with it. To prevent that, we need encryption to provide confidentiality, which ensures that the data is only accessible by the client and the server. But what if a man in the middle intercepts the encrypted data? Although they can't read it because it's encrypted, they could still modify it. At this point, we need integrity, which ensures that the data has not been modified between the client and the server. We achieve this using hashing algorithms like MD5, SHA-family, and other hashing algorithms. But again, how can we prove that the client or the server is really who they claim to be? This is where public key infrastructure, PKI, comes into play. Now we have 3 concepts that need to be present to confirm that data sent across the wire is secure and protected. We have confidentiality, means data is only accessible by the client and the server, and we use encryption algorithms for that. We have integrity, means data is not modified between the client and the server, and we use hashing algorithms for that. We have authentication that proves that the client and, most important, the server are indeed who they say they are, and we use a PKI for that. Great. We have kind of a general idea of how TLS makes sure that the data sent across the wire is protected. But what actually happens? How the encryption confirms confidentiality, and how hashing confirms integrity, and how a PKI confirms authentication. Now, let's get into how hashing verifies the integrity of data. I am sure that you have heard of MD5, SHA-1, and the SHA-family. So let's say we have a client that wants to send data to the server. Now, if someone is in the middle, he can intercept that data and tamper with it. We use hashing to confirm that the client is the entity who sent the data. But how? Well, the client will hash the message, for example, using MD5 algorithm, as we do in Linux. We're going to hash the message hello, and then send the hash value of the message and the clear text message to the server. The server will take the message, calculate the hash value. If it's the same as the one sent by the client, then the data was not modified, and indeed the client is who claims to be. But what if a man in the middle captures the data, change it, and then calculate the new MD5 hash of the new message and change it also? Then the server will take the message, calculate the hash. It is indeed the same as the one in the package, which means the message is from the client. But that's not true. To fix this problem, the server and the clients, before even exchanging messages, they need to establish a key. So this key will be known only by the client and the server. We're going to talk about how this key is going to be established later on in this course. And then when the client sends the message, the hash calculation will be the key plus the message. Then the client sends the message and the hash value without the key. And then when the server receives the message and the hash, he will take the key, add to it the message, and then calculate the hash value and compare it with the hash value sent in the client request. So even if a user intercepts the client request, he can't create the correct hash value because he don't know the key. This technique that we just discussed is called MAC, Message Authentication Code, because it validates the integrity, which means that no user in the middle was able to tamper the message since he didn't have the key. And also, it ensures authentication because the only clients that can send a valid message and the hash is the client who holds the key. So with this method, we ensure data integrity and the authentication of the client and the server. Now, as we said before, the client and the server needs to agree on the key, but they also need to agree on how the key should be combined with the message. Because if the clients calculate the hash of key plus message and the server calculate the hash of message plus key, there is no way those two values gonna match, even that it's the same key. So the client and the server must agree on a key and also the combination of the key and the message. So the industry standard implementation of MAC, which means how the key and message should be combined, is called HMAC, Hash-Based Authentication Code. And that's how SSL TLS provides data integrity. Now, let's explain how encryption is used in TLS to provide confidentiality. As we said before, encryption is used to provide confidentiality. But how? Well, I am sure you know that there are two types of encryption, asymmetric and symmetric. The asymmetric encryption uses two keys. If one is used for encrypting the data, the other is used for decrypting it, like the RSI algorithm. So let's say we have two users, A and B. User E wants to send a message to user B while nobody in the middle sees or tampers the message. With asymmetric encryption, user E will generate two keys. One is used for encrypting the data, and we call it the public key, and the other key is used to decrypt the data. That's called the private key. But you need to know that if I encrypt the data with the private key, I can decrypt it with the public key. So with whatever key I used for encryption, the other key will be used for decrypting the data. So both user E and B generate their own public and private key. User E will use user B public key to encrypt the message, so when the user B receives it, he will decrypt it using his own private key. And this is how asymmetric encryption is used to provide confidentiality. But we can't use asymmetric encryption for data protection since it has some weaknesses. First, it's slower because it requires much large key sizes. Also, in asymmetric encryption, we have the ciphertext expansion. So whatever you encrypt with asymmetric encryption, it ends up larger and larger. And that's why we also have symmetric encryption, where there is only one key used to encrypt and decrypt data. So if user E wants to send a message to user B using symmetric encryption, first of all, they need to establish an encryption key. And then user E will encrypt this data with that key, and user B will decrypt it with the same key. That's faster than the asymmetric encryption, but also it's less secure because that key is being shared on the wire, and if someone captures it, he can decrypt all the data. To fix this problem, we have what it's called hybrid encryption, which means we use both encryption methods. We use the asymmetric encryption to establish the symmetric key between E and B, then we use symmetric encryption to exchange the data. So now, even that we have choose symmetric encryption to encrypt the data, but the key can't be intercepted by an entity in the middle since asymmetric key was used to exchange it. And that's how the SSL TLS protocol provides confidentiality. It uses both encryption types for data protection. As we mentioned it before at the beginning, there are 3 checks for SSL TLS: confidentiality, which is provided by encryption; integrity, which is verified using hashing algorithms; and authentication, which is provided by the PKI, the public key infrastructure. But we still don't understand what a PKI is. Let's say we have a website called bank.com and the client is a web browser. The client wants to send data to the web server securely, so they use symmetric encryption for confidentiality and HMAC for integrity. Both of this requires a mutual secret key between the client and the server. Before we can apply symmetric encryption and MACs, we must establish a symmetric key. We have learned that asymmetric encryption will be used for secure key exchange. So the server generates a set of asymmetric keys, a public and a private key, and the client also generates its own asymmetric keys to exchange the symmetric key. Great. But there is one more thing we need: authentication. Any server like the one in our example, bank.com, can generate asymmetric keys using various tools that we will explore in this course. But how does a client, like a web browser, know that the server is who claims to be? How can the client trust that it's not communicating with an imposter? If the web server claims to be bank.com, how can we confirm that as a client? This is where the CA, Certificate Authority, comes into play. A CA is a trusted entity that issues digital certificates. The client trusts the CA because the CA public key is stored in the client web browser. There are many CAs like DigiCert, GoDaddy, GlobalSign, and others. The CA generates its own public and private key, and when the server, bank.com, wants to prove its identity to the client, it sends a certificate signing request, a CSR, to the CA containing the server public key and information about its identity. The CA then signs the server public key with its private key and issues a digital certificate to the server, in our case, bank.com. Now, when the client receives the bank.com certificate, the client browser can verify that it was signed by a trusted CA using the CA public key, which is, as we said before, stored in the browser. So, if the certificate is valid and matches the domain bank.com, the client can trust that the server is indeed bank.com because the client trusts the CA and the CA vouches for bank.com. Notice that all 3 components, the client, server, and CA, are crucial for making this work. These 3 key players form a triangle known as the PKI, or public key infrastructure. Anytime you have a client, server, and the CA working together, you have a PKI, and that's how PKI provide authentication. Again, 3 entities form the PKI: the client, server, and CA. Clients need to connect securely or verify an identity, server needs to prove its identity, and the CA validate identities and generate certificate. Most of us are familiar with the PKI for web. In this scenario, the client is the web browser. The server may be a website like bank.com, and the CA could be an entity like GoDaddy, Sectigo, DigiCert, or Eden Trust. However, PKI is not limited just to web security. There is also a PKI for email sign-in, code sign-in, and so on. For example, when you try to install a software in Windows, if it's not signed with a trusted certificate, you will see a warning like the one in the screenshot. On the left, Windows is showing you that the software is signed by Mozilla Corporation, which means it was signed with a certificate issued by a CA that Mozilla uses. Here, your computer is the client. Need to verify the software identity before allowing it to run. The software is acting as the server in this analogy, wants to prove its identity, and the CA that issues the certificate used for signing ensures this identity is valid. If the software is not signed, then you're gonna get a warning like the image in the right. As you can see, in an internal corporate environment, companies may need their own PKI for internal purposes like code sign-in, email sign-in, or securing local web applications. This is where an organization can implement and set up its own CA to sign and create certificates for its internal resource. This brings us to ADCS, Active Directory Certificate Services. So ADCS is a Microsoft implementation of a PKI, integrating with Active Directory Forest to prevent a range of services from encrypting file system to digital signatures and user authentication. By the way, I have a Windows Server 2019 where I'm going to install ADCS and another Windows Server 2019 where the domain controller is already installed. The name of the domain is bank.local, and the machine where I'm going to install ADCS is server.bank.local, a domain joined machine. To install ADCS, we go to Add Rules and Features, click Next, 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 Then we select Active Directory Certificate Services. Then we select all the role services including the CA web enrollment, and other features. Hit install, couple minutes, the installation is successful. Now we need to configure the ADCS on this machine. Hit Configure Active Directory Certificate Services, click Next, we select Role Services to configure. As you can see, some of those services are not going to be configured for now since it requires some other features to be installed first. But we will get back to it later. Click Next, then we select Enterprise CA since we are in an enterprise environment, which is Active Directory, not a standalone one. Hit that Next button the same way you hit that Subscribe button at the beginning. Then we choose a root authority, create a new private key. Because this is the first CA being created, I will select the second option if I'm joining an authority. But in our case, I am creating one. Now I will choose the algorithms for sign-in certificate, RSA, then we click Next. As you can see, those are the default common names created. Then we choose how long do I want the certificate to be valid. The default is 5 years. We'll leave the default certificate database path and we click Next. Finally, hit Configure. We wait a couple minutes. As you can see, everything is configured correctly. Then asks me if I want to configure additional roles and services. Choose yes, and we choose the two options that were not installed before. Then it asks you for a service account, which is a domain user that is a member of the IIS users local group. I have already created a user called ADCS services. There is a member of the IIS users local group, as you can see, successfully added. Now let's click Next. I will change the country and leave the other fields empty. We click Next and we select again the ADCS service user, Next and Configure. Now restart and you have ADCS installed in your AD environment. I want to show you one thing regarding the utility of ADCS, just to get a better understanding. So I have the default Apache web server in my Kali machine that is not using an SSL certificate. I'm going to create a self-signed SSL certificate, which means a certificate that is not signed by any trusted certificate authority. I'm going to use the OpenSSL command with a couple options. We start with the rec option. That means we want to create a certificate sign-in request, a CSR. Then we specify -X509. This option tells OpenSSL to generate a self-signed X.509 certificate. Then -nodes option, which stands for No Data Encryption Standards. This flag tells OpenSSL to not encrypt the private key with a passphrase. Then -days 365. In this case, the certificate will be valid for about a year from the date of creation. Then we have -keyout option, which specifies the output path for the private key. The private key is saved with the file name debian.key. By the way, the private key is essential for decrypting the SSL TLS traffic. You should protect this file carefully. And we have -out, which specifies the output file for the self-signed certificate. The certificate is saved with the file name debian.cert. It holds the public key along with other information such as the issuer, validity period, and other metadata. This file is what you share with others to establish secure connection. We hit enter and set the fully qualified domain name to kali.bank.local. This attribute is very important. You will see why in the next couple minutes. Hit enter. As you can see, we have the debian.cert and debian.key, which is the private key. Now let's move the SSL certificate to the certificate directory and the private key to the SSL private keys directory. Let's change the owner of those files into www.data. Now let's add this newly created SSL certificate to the default SSL configuration of the Apache server. Let's turn on the SSL engine and set the SSL certificate file to debian.cert and the SSL certificate key file to debian.key. Restart the Apache server and then open the website with the HTTPS protocol. As you can see, we have got a warning saying that this certificate is not signed by a trust certificate authority. If we go to view certificate information, you will see that there is no CA that signed this cert. Now let's get my IP address and access from the Active Directory environment. I have added the kali.bank.local domain in the DNS server on the domain controller so I can access to the Kali web server from any domain joined machine. As you can see, we have got a certificate error. Now let's fix that error. Let's remove those two files. Then we create now a CSR, which is a certificate sign-in request. It's not a self-signed certificate, but a certificate sign-in request, which means we're going to send it to the certificate authority and it will be signed by it. So when I use it, we will not get that SSL warning message because the cert is signed by a trusted CA. Hit enter. We specified fully qualified domain name as kali.bank.local and then a password. As you can see, we have a certificate signing request and the private key. If you still remember, at the ADCS installation, we have installed the web enrollment service. So we can sign the CSR certificate using the web enrollment interface. So we go to this IP address of the CA, the server where ADCS is installed, /cert srv, and we specify the credentials of the user that has the right permissions. We will take a look at those permissions later. I will just use the lower priv user, which is a user that has no special privileges. But before authenticating, I need to create what's called a certificate template. A template is basically a blueprint for a certificate, which means if I am going to request a certificate for server authentication, like the one we need now, there is a template for it, so we don't need to create it from scratch. There are a lot of templates for different needs, like code sign-in, email sign-in, client authentication, and more. In our case, we need a template for a web server authentication EKU, and an EKU stands for extended key usage, which means what is the objective of this certificate template, or what is the purpose of it. So each EKU, let's say server authentication, is identified by an OID, an object identifier. For example, this OID is for the server authentication EKU that is used to authenticate a server identity. So certificate with this EKU ensures that the server presenting the certificate can be trusted by the client, which is called web server. But let's create one to also understand how templates are created. Select the certificate authority, then certificate template, right click, select manage, choose any template. I'm going to choose the web server one to keep things simple. Right click and duplicate. We call this Kali web server, so we can use it for our Kali web server. Then we move to security. As we can see, the domain users can enroll to the certificate, which means any domain user can sign a CSR certificate of a web server. If we go to the extension tab, application policy, we see that this template EKU, or the purpose of it, is server authentication, which is exactly what we need. And the reason why we have got that is because we have duplicated this template from the web server template. As I said before, we can use the web server template, but I just want to show you how to create one. We import the Kali web server template, and it's enabled now. Now, let's authenticate to the web enrollment side with a domain user that has low privileges. So go to the IP address where ADCS is installed, /cert srv. We authenticate using the low privilege domain user. We are in. Then we select the user certificate, and then we select the template, which is the Kali web server. And we copy the certificate sign-in request and paste it in the requests field. Then we click submit, and we download the certificate. Let's move it from the download directory to the current directory. And we will replace the private key with our new generated private key as we did before for the self-signed cert. And also we replace the certificate with the cert new.cert that we have downloaded from the web enrollment interface. Now we add those certs in the SSL config file the same way we did for the self-signed certificate. Restart the Apache server and go to the local host. Let's check certificate informations. As you can see, it's signed by bank server CA. Now, if we open the kali.bank.local domain in our Active Directory environment, we will not get that error message because the browser trusts the CA and already had its public key stored to verify the certificate. Great. We all know that Kerberos is a widely used authentication protocol designed to allow secure access to services over the network. Kerberos relies on ticket to authenticate users and services, with the goal of minimizing the need to repeatedly transmit sensitive credentials like passwords. I have already made a video explaining pretty much everything you need to know about Kerberos in the context of Active Directory and how it works. But let me give you a quick overview. First of all, we have the initial authentication. The client sends an authentication request to the KDC, an ESREC. Then the KDC verifies the user credentials, and if valid, it responds with an ESREP, which includes the TGT encrypted with the KDC secret key, the key RBTGT password hash. Then, if we want to access a service like SMB, MSSQL, the client uses the TGT to request a service ticket, a TGSREC, from the KDC for the specified service. The KDC responds with the service ticket TGSREP, which the client uses to authenticate to the requested service. While Kerberos is secure, Its traditional method of authentication relies on password-based encryption to generate cryptographic keys. This introduced several weaknesses like password vulnerabilities, so passwords can be guessed, stolen, or brute force, especially weak or reused passwords. The security of the initial exchange heavily depends on the strength of the user's password. That's why PKInit is being introduced. Public key cryptography for initial authentication. It's an extension to the Kerberos protocol. So PKInit enables Kerberos to use public key infrastructure, PKA, and certificates for the initial authentication exchange instead of relying on passwords. So PKInit implements certificates which replace passwords in the initial authentication, which can significantly reduce the risk of password-based attack. Also, PKInit integrates with certificate authority to issue and validate certificates. Organizations using Active Directory Certificate Services, ADCS, can manage the life cycle of certificates, ensuring that only trusted users and system can authenticate to the KDC. As we said before, the PKA proves the identity of the client and the server. The use of CA-issued certificates ensures that the KDC trusts the client and vice versa, reducing the chance for unknown devices or users accessing the network. So the first attack we will start with is SC1, which is an abuse of a misconfigured template that elevates our privileges to a domain admin. But how does it work? Well, this template must have enrollment rights enabled for the user we control. In our case, the low privilege user that we control. Also, the enrollee supply subject attribute is enabled. And that's actually the abusing part, because if this attribute is enabled, then any user that have enrollment rights can request a certificate of any other domain user, including domain admin. The third condition is the template should have the client authentication EKU. Now, to get a better understanding, I will start by creating a template called SC1. Then I go to the security tab and then allow the domain users to enroll to this certificate. So this will allow any domain user to enroll, including the low privilege user. Then I go to the subject name tab and then check the supply in the request attribute. And that's what's going to allow us to request a certificate of any other domain user. Let's apply those settings and import that template. And then if we check the EKU, the purpose of this template, by default, the user template that we duplicate at the first place has client authentication, secure email, encrypting file system EKU. So it contains the client authentication, which is what we are interested on. Great. Now, let me show you how can we use this to escalate our privileges from a low privilege user to a domain admin. I am running the CMD process as the low privilege user in bank.local domain. We will start with enumerating the Active Directory Certificate Services, and we're going to use Certify from Spectre Ops. This tool will allow us to enumerate, find vulnerable templates, and abuse them. It sounds interesting. All right, let's start. So to just enumerate ADCS, we use certify CES or we type certify find, and it will get back to us with the certificate authority name and all the templates. So certify find, as you can see, we've got a lot of output. Back in time, I had no idea what all of this text means. Thanks to this course, it all makes sense to me now. If you take a look at the end, you will find a template called SC1, which is the one we have already created. As you can see, the enrollee supply subject is enabled. And also, in the enrollment rights, domain users can enroll to this certificate. And we have client authentication in the extended key usage, EKU. That's mean that we can use this certificate for authentication. And because of the enrollee supply subject attribute enabled, we can get a certificate in behalf of any other user, in our case, the domain admin administrator. We're going to use this command, certify, then request, because we are requesting a certificate. Then we specify the certificate authority, just copy the name from here. Then we specify the template we want to abuse, which is SC1, and then the alt name, which is the alternative name that we want to impersonate and get its certificate. In this case, it's the administrator. That's it. We hit enter, and couple of seconds, we've got a private key and the public key, the same way we used to do with OpenSSL. Now, this certificate is issued by the CA, and we can use it for authentication. Why? Again, because the EKU of this template is client authentication. Who is responsible for authenticating us? Let's see if you still remember it. Great, the PKInit. Now, this cert is in the PEM format and we need to convert it to a PFX format so we can use it for authentication. Let's copy it and paste it in a file, call it cert.pem, and then we use OpenSSL to convert a PEM format into a PFX format. We're going to use this command and we specify the cert.pem that we have already saved. We enter a password, converted successfully. Now we can use Rebus tool to use the certificate to authenticate, and this way we're going to get a TGT as the domain admin administrator. So Rebus, then we use ask TGT option to get a TGT, then we specify the user, which is the administrator, and the domain, which is back.local, also the PFX certificate, and the password we have set for that certificate before, and then the DC. Also, we specify the no wrap to not get new lines in the terminal, and PTT to pass the ticket to memory, so I can use it to authenticate to the DC. Hit enter. As you can see, we have got a TGT as the domain admin administrator. If I type keylist, as you can see, we have the TGT. And now I can get into the DC SMB share. We can also use enter PS session to the DC, and we are in. Now, the next attack is SC2, which is an escalation technique that will also allow us to move from a low privilege user that have enrollment rights to a domain admin. SC2 is very similar to SC1. The difference is that in SC1, we need client authentication EKU, and in SC2, we need the any purpose EKU. The any purpose EKU primarily allows an attacker to get a certificate for any purpose, like client authentication, server authentication, code signing, etc. And we are interested in the client authentication EKU. This way, we can downgrade SC2 to SC1. So let's do it. To not waste time, I have already created this template. I called it SC2 so we can identify it easily in the certify output. As you can see in the security tab, domain users can enroll for this certificate template. And if we go to extensions, in the application policies, we have any purpose. And also, don't forget that we have the enrollee supply subjects enabled, so we can request a certificate for any domain user. And the abuse is the same as SC1. Since we have any purpose EKU, means that we can use the certificate for any purpose. So certify, find. As you can see, we have SC2 template and the enrollee supply subject. And in the EKU, we got any purpose. It's tut object because my CMD is in French, but in English, it's any purpose. And also, domain users can enroll to the certificate template. So let's start by typing certify, request, because we are requesting a certificate, and then we specify the CA, and the template we want to abuse, then the alt name attribute so we can get a certificate of the administrator, and we specify the domain, which is bank.local. We have got the certificate. Let's convert it to a PFX format. And then we use Rebus to ask for a TGT using that certificate the same way we did before. Now we have got the TGT. Now we can get to the DC. Amazing. SC3 is kind of the same as SC1 and SC2, but we have different EKU. So the certificate request agent EKU, known as enrollment agent, allow an entity or a user to enroll for a certificate on behalf of another user. And that's very common in enterprise environments. Sometimes you need an administrator, for example, to enroll a cert on behalf of a new employee so he can authenticate. And ADCS accomplish this through a certificate template with the certificate request agent OID in its EKU. Means if a template has this OID in its EKU, users that has enrollment rights to it can request certificates on behalf of other users. In our case, domain admin. To abuse this for privilege escalation, a CA requires at least 2 templates matching conditions below. So template 1 must have the enrollment agent EKU that we mentioned before, and the user that we control can enroll to that template. Also, the manager approval is disabled. If manager approval is enabled, a certificate is placed in a pending state until a user with the CA manager role allows its issuance. Also, no authorized signature are required, which means this attribute must be set to 0, so no need for any enrollment agent to sign our CSR. If it's greater than 0, auto-enrollment is no longer possible. The second template must allow the user we control to enroll. Also, manager approval is disabled, and the certificate template defines an EKU that allows for domain authentication, along with the certificate request agent EKU enabled. So certify request CA server.bank.local bank server CA template SC3. With this cert, we can't do domain authentication because it's not included on its EKU. So we will just use the enrollment agent certificate to issue a certificate request on behalf of another user to a template that allows for domain authentication. So certify.exe request, we specified CA, then the second template, then on behalf of, which is the administrator, and then the certificate, and then the password we set for the certificate and the domain. And now we can use reviews to get the TGTUs in the certificate. Cool. Now, let's talk about one of the most interesting privilege escalation technique, which is SC8. When we installed ADCS, we have checked the web enrollment box, and that allows us to enroll certificate from the web as we did before. By default, those web enrollment sites allow authentication through NTLM, and that's bring us to the possibility of relaying that NTLM authentication to other services. I am not going to go through relaying in deep, but feel free to leave a comment and let me know if you want a full video about it. Maybe building the PUTM or DFS course to get a better understanding. Let me know in the comments below. So basically, we have NTLM authentication enabled in those web enrollment sites. That means I can intercept the domain computer or user NTLM authentication from a different device and relay it to the web enrollment site, and then grab a certificate as that user. Now we can listen and wait for a high privilege user to authenticate to our machine and then relay that to the web enrollment interface, or we can coerce it to do that, which means we force that machine to authenticate to our attacking machine, and then we can relay that to the web enrollment interface. So let's do it. First of all, if we just curl the web enrollment interface that we used before and take a look at the headers, we will see NTLM is allowed. I'm going to set up an NTLM relay server that is listening for all known protocols. We specify the target that we want to relay that NTLM authentication to, which is the web enrollment interface. Then we specify the template we want to abuse after, like we authenticate to the website, and --ADCS, just to mention that this is an ADCS abuse. There we go, we are listening now, and all we have to do is for the domain controller to authenticate to our attacker machine. So the relay server intercept that. We're going to use the DFS coerce Python script. The core idea behind that tool is based on forcing a Windows machine, typically a domain controller, to initiate a connection to our attacker machine. But why is that possible? Well, several Windows protocols such as MSRP-RN, Printers Polar Service, MSFS-RVP, File Share Shadow Copy Service, MSEFS-RPC, encrypting file system, and MSDFS-NM, distributed file system, allow an authenticated or low-privileged user to interact with the services. Many of these services make the DC or the target machine authenticate back to the calling user. This tool automates this by calling a variety of DCE, RPC, distributed computing environment, remote procedure call services that leads to the target authenticating against the attacker machine. As I said before, if you want me to make a deep dive video about it, let me know in comments. Alright, let's use it. So Python 3 dfs chorus.py-u low privilege user -p password. Then we specify the attacker machine and then the target machine that we wanted to authenticate to our attacker machine, which is the DC. As you can see, we have received a connection from the DC and we are attacking the CA server. And at this step, it's successfully authenticated to the web enrollment interface, then generating the CSR, the certificate signing request, while choosing the domain controller certificate template. And then, after the certificate is signed by the CA, we extract it. As you can see, we have got a DC $.pfx. $sign means that this is a machine account. Since we forced the DC to authenticate to our attacking machine, that means that the domain controller machine account is what's going to perform the authentication. With that certificate, we can get the NTLM or TGT of the domain controller machine account, and then we can perform a DC sync attack. So we're gonna use the PKInit tools, which will allow us to authenticate using the PFX certificate and grab a TGT. So get TGT PKInit.py, and we specify the PFX cert, then the user, and the file where I want to save the extracted TGT. Then we specify the IP address of the domain controller. We have got the TGT in the file.c cache. Let's export it to the krb5ccname environment variable. Let's check if it's imported using keylist. As you can see, we got it. Now we can use secrets dump to perform a DC sync and extract the domain administrator NTLM hash. We got it. And let's use WinRM, and we are in the DC. Great.